Hey everybody, let's go through this practice test. I meant to try to come in today and encourage you guys, but my wife is on like 2 hours of sleep, and so this is kind of the best I can do right now. I'm gonna go kind of fast, so use your pause button, I guess, and I'll also try to put pictures of the front and back so you don't have to watch the whole video if you don't want to. So firstly is that all the underlying terms are fair game for being just asked to draw or give an example of or define. And so it says define atmospheric pressure. So that would be the force, I'm trying to use different words, from the atmosphere's weight. So the atmosphere is made up of lots of atoms, nitrogen mostly, and they all have mass. And they're all pulled on by gravity. You can hear Saya in the background there. My daughter is taking a nap, and Saya has a friend. Okay, the force from the atmosphere's weight. Saya's climbing on me to see. Hi Saya, you want to say
Hi.
hi? Okay, next problem, converting pressure units. So you always start with the number and the unit given to you in the problem. Try to copy the whole thing so that you don't mess up on sig figs. And then multiply by a fraction. The unit that you start with goes on the bottom to cancel out. The unit that you want goes on the top. And you can always convert right from one to the other, and there's not any two-steppers in these kinds. And then you can find these numbers on your equation sheet. You probably haven't seen the equation sheet yet. When you see it, when you take your test, it'll be pretty easy to find stuff. So there's a whole section for gases, and it has 1 atmosphere is 760 millimeters of mercury equals 760 torr, and it says STP is 0 degrees Celsius in 1 atmosphere, and it says what R is in the ideal gas law. Okay, so anyway, 1 atmosphere is 760 millimeters of mercury. We can decide these are exact. I look up every year whether they are or not, and there's one either millimeters of mercury or torr that is, and the other one's almost, so that's close enough. Okay, so then check your units cancel out, and you're doing 0.5 times 760, divide by 1. And so you get 380. I should have 2 sig figs, so if I don't put a decimal at the end, it's already correct. Last zeros don't count as sig figs unless there's a decimal, so 1, 2, no. So 1, 2, 380 millimeters of mercury. Okay, part C says, draw an example of vapor pressure. So like if I have a pot of water and I am boiling it, so it gets hotter and hotter. At first there's a little bit of water evaporating, basically, and then as it gets hotter and hotter, there's more water evaporating. And then eventually the pressure gets to be enough so that the pressure of the liquid turning into gas is equal to atmospheric pressure, and then it boils. Then the liquid feels free, it doesn't have all that pressure on it, so it makes all those bubbles right in the liquid. We'll learn about that more in a different chapter. So vapor pressure is pressure from a liquid turning into a gas. Next question says, what's the volume of 1 mole of gas at STP? Problems like this don't look like they have enough units or numbers in them, but STP is its own numbers. It's on your equation sheet. That means standard temperature and pressure. That's 0 degrees Celsius and 1 atmosphere of pressure. Somebody made that up, so those are exactly 0, exactly 1. Okay, so when I'm given a temperature and a pressure and a mole, and I'm asked for the fourth thing, then we use PV equals nRT. I'm trying to solve for volume, so I'll divide both sides by P and get V equals nRT over P. Hi, Saya.
Saya's making cards.
You want to show them a card?
Yeah.
Okay.
So
I'm going to put it over here. Saya has a card to show you. Ooh. How did you make that, Saya?
well, I'm gonna show you. We're gonna do one of them on the table.
So this is the N for moles. This is your temperature, but you got to add 273 to convert to Kelvin. So this is 273 Kelvin. This is your pressure is 1 atmosphere. And then R is 0.0821 atmospheres times liters over moles times Kelvin. So to solve for V, we are doing 1 times R times 273 divided by 1. So 1 times 0.0821 times 273 divided by 1. I got 22.4133. So this is 3 sig figs. This is a measured value. So if we're rounding this much, it's 3 sig figs. This is 3 sig figs. This came from STP, so that's infinite. The reason this is 3 instead of infinite now is because we added 273. This is rounded, it's really 273.15, and it keeps going. That's a measured value also.
I'm gonna show him how.
So looks like 2 sig figs is gonna be, for my answer, 1.0, so that'd be 22 liters. You gonna show us, Saya?
Yeah, as soon as we're ready.
Oh, okay. Saya's not quite ready to show you his machine for making that card. Okay, so next one is talking about how different gas measurements are proportional to each other. So it's a closed rubber balloon. So sometimes students get all clever and say, well, some's going to leak out. And yeah, that's true, but not very fast. So let's just say it holds the air.
Can I sit in the lap? No.
Saya's going to sit in the lap.
Yeah. I'm gonna put this white under.
Like this. I guess we can tilt it like that so you can see.
Look.
So you put the paper in that hole?
Yeah, but it needs to have these 2 black things over it to make it taller for that.
It needs to have black things in there
Yeah.
to make it taller.
So I'm gonna show you
Black thing.
how to do it. So how you do it is you get this paper and you well you put got that pin down, but not this permanent marker. Just
Okay.
that pin down.
Yeah, we
there.
only dropped the pin, not permanent marker.
So now we put it here, and then
Oh, so you have to make each part of the card, each little part? Wow.
yeah, and then you have to put. I have to put it on again because that as we flipped out. And then put this here. Then
Okay, let's move the machine so you can do it. Is this a good spot for the machine?
yeah, I'll then put this
Oh, you
next
sandwich it.
black thing here. Then you put it in the machine. I'm gonna show you how you make it black and do it.
Is it doing
It's
something?
Going through.
Yeah, you probably have to push it in more. Yeah, I understand if you guys need more time to figure out how to do this part of your test. It looks kind of complicated to put all these
It's
things together.
going. I'm gonna show ya.
Well, there it goes. Okay.
It's inside. But
It almost came out.
it came out. Let's open it.
Oh, yeah,
Up
right.
and-
Look at that.
Ta-da!
Thanks for showing us, honey.
That's how we made the cards.
Sure is. Okay. Thanks for showing us, Saya.
Yeah.
Good job, Precious. Okay, so it's a balloon with some air in it and it cools down. So when it cools down, then the particles move slower and the average kinetic energy decreases. When it cools down, it moves slower and the average kinetic energy decreases. That means the particles hit the sides of the container less often, so pressure decreases. When it cools down, particles move slower, hit the sides of the container less often, so that means there's less pressure keeping the balloon out, so the volume will shrink because it's still pushed on by atmospheric pressure. The gas is getting closer together because the volume is decreasing. The moles are staying the same, so we're assuming they're not getting out of the balloon. And finally, attractions between molecules, because they're getting closer together and because they are moving slower, they're spending more time by each other, so that will increase the attractions between molecules, which is why if you get it cold enough, eventually the air condenses and you have liquid air, liquid nitrogen, liquid oxygen, liquid other stuff. If the problem says to assume that it's an ideal gas, then the attraction would still say 0, but ideal gases are pretend. Okay, 2C says 2 grams of helium, or STP, was the gas density. Makes me happy to see problems like that don't have very many numbers in them, because it really does have numbers, but they're hiding in there. You have to be clever. Okay, so gas density, we need to know the units are grams per liter. That's the hard part of the problem, is knowing that this gas density is grams per liter, or if asked for molar mass, that would be grams per mole. So we have the grams, 2 grams. So I need to solve for the liters. So I'm going to use PV equals nRT. I'll use V equals nRT over P.
First, we need to put
R is still 0.0821 from the previous problem. It's up there. It's on your equation sheet. Temperature is, like the previous problem, 273 Kelvin, because it's at STP. Pressure is 1 atmosphere, just like the previous problem, because it's STP. Standard temperature and pressure. Moles I need to solve for. So my moles, I have the grams, and I know it's helium, so I can use the molar mass to solve for the moles. So convert from grams of helium to moles of helium. I think that's the right number. I didn't look it up. Okay, so this would be 0.50 moles. Okay, so we're going to say 0.50 times 0.0821 times 273 divided by 1. And that will get our liters. And then we take our grams divided by liters, and that'll be our final answer. So the volume is... The volume is 11.20665 liters. That should have 2 sig figs, so I'll remember it's 2 sig figs. And then let's write it down for now. 11.20665 liters, 2 sig figs. Okay, so the density is going to be my mass over my volume in grams per liter, so that is 2.0 grams over 11.20665 liters, and 2 sig figs, my answer will have 2 sig figs. So 2.0 divided by, that answer is 0.18 grams per liter. Okay, sorry you couldn't see, all I did was divide there like that. Okay, next page. It says, what's the density of ammonia, NH3 at STP? So again, I need grams and I need liters. I'm given that the temperature is 273 Kelvin. I'm given that the pressure is 1 atmosphere. So I need to solve for volume, which means I need moles. I actually have moles, it's not obvious, but it says it's NH3, which says I can look on the periodic table and find the molar mass. So for NH3, I know that 1 mole is can be my N, because then that has a mass, a molar mass of 17.04 grams when you add up nitrogen and 3 hydrogens. So that problem doesn't look like it has any numbers, but it really has everything you need. So density for gases is grams divided by liters. So I have the grams, and I'm going to solve for the liters again, just like in the last problem. So V equals nRT over P. So I'm going to do 1 mole exactly, because I'm using the molar mass. R 0.0821, that's 3 sig figs. 273 Kelvin, that's 3 sig figs. 1 atmosphere, that's infinite sig figs. So again, I guess it's same math as we did before. This number that I got on my calculator is called standard molar volume. That's the volume of 1 mole of any gas at STP is this volume. So that's a shortcut you can use, like a conversion fraction if you want. Okay, so volume is 22.4133 liters with 3 sig figs. And so my density is 17.04 grams divided by 22.4133 liters. This is 4 sig figs, this is 3 sig figs. So my answer is going to be 0.760 grams per liter. This 0 is part of my significant figures because there's a decimal anywhere in the number. Next problem says, gives you mole of one chemical, asks for volume of a different chemical. So to convert between chemicals, we need a mole ratio. I get the mole ratio from my balanced chemical equation. So start with the number of moles given to me in the problem. Moles of O2 go on the bottom to cancel out. Moles of water go on the top to give me what I want. I get the numbers from my balanced equation. It's 1 and 2. So this is 2 moles of water. Then I'm trying to find the volume of water. It's a gas at 900 degrees Celsius. So that is V equals nRT over P again. This is my moles here, the 2 moles. That I guess has only 1 sig fig. That's kind of a silly problem. My R is again 0.0821 atmospheres times liters over moles times Kelvin. My temperature is 900 degrees Celsius plus 273 to convert it to Kelvin. I guess that's actually not that of sig figs then, because when you add, you don't count sig figs. So this is going to be 1173 Kelvin with 4 sig figs. That doesn't seem right, huh? But that's how the rules say for sig figs. Okay, and then oh, oops. I guess we needed pressure and I didn't give it to you. Sorry about that. So we're assuming we have normal atmospheric pressure, I suppose. And so we're just going to say pressure is 1 atmosphere. Sorry about that. I'll text Miss Block right now and tell her about that so that's not so confusing to you. Okay, so we need to calculate the volume and then we're done. Okay, so this is the answer I got. That'll be in liters because the units of R are atmospheres times liters over moles times Kelvin. Everything cancels out except for liters. This would be better if I guess if I wrote all these numbers with units, you could see how they canceled out. But the main thing about the units in these problems is just to remember to always use atmospheres for pressure and liters for volume and Kelvin for temperature. If you use different units, then you're using the wrong R value. Okay, so that would be 192.6066, but round to 1 sig fig. So that would be 200 liters. 1 sig fig, placeholder, placeholder. You can write it like 2 times 10 to the second liters if that makes you happy. Okay, 3a, define volatile liquid. That would be a liquid that turns into a gas more easily than water. Most definitions just say readily or easily, but what we compare it to is water because it's so common. So if it has less attractions than water, then it'll have an easier time of vaporizing, and we'll call it volatile. So an example would be like acetone nail polish remover. If you put it on your skin, it evaporates very quickly. It feels cold because evaporation is endothermic, so it uses heat from your body to do that process. Okay, part B. If you use the ideal gas law to solve for moles of water, which you know is a liquid at room temperature because it has high attractions between the particles, then you are assuming that there are no attractions. And of course, in real life, there are real attractions. So I'm going to pause while I think for a second so I don't mess this up. Okay, I figured it out. So we're solving for moles. That's N equals PV over RT. And this is meant to be like a lab that there's a YouTube video for. There's a link on your study guide answers. And then, so if there's some water vapor in here that we want to know the moles of, then we're assuming it has no attractions, so the particles are spread out, and the pressure in there when the particles are spread out is equal to the atmospheric pressure. And so this is just atmospheric pressure. That doesn't change based on particle attraction. This is the volume of the flask, that doesn't change. This is temperature of the gas in the flask, that doesn't change. R is a constant. So all of these are okay, but if there are attractions, so if it's a real gas, if there are attractions, then there would still be a gas occupying that volume, and it would still be at that temperature, and it would still leak out of the flask until the pressure was the same as the outside because we poked a hole in it. But what would change is if there's attractions, then more of it would fit in because there's attractions. They would be attracted to each other, and they would be hitting the sides of the container less often because of their attractions, because they're attracted to each other. And so there would be more gas in there. So more than the ideal gas law would calculate. So my moles would be too low. So that's a tricky problem because you can't really figure it out with the math equation very good. You have to think about the attractions. The reason is because the attractions aren't in that equation. Okay, now we get to the easy stuff. What we did so far, I guess, wasn't really very hard. It's definitions, so that's kind of tricky about stuff you can't see. And then it's PV equals nRT, and the only thing about PV equals nRT is you have to use Kelvin, you have to use atmospheres, you have to use liters. Sometimes people can't rearrange this equation, so practice with that if you need to. Okay, so that was a little pause what I was saying is the rest of this is partial pressures and diffusion and fusion is super simple. Pressure of a gas, if temperature and volume, if temperature and volume are constant, depends only on the number of particles. If there's more atoms, molecules flying around, then they exert more pressure. So these are not new problems, they're just like moles. So you could say this is like moles of oxygen, and this reaction changes from 1 atmosphere or 1 mole to half a mole. So how many moles of water are formed? So it's just that like that problem, except we're going to do it with pressures. So if we subtract these, then I find out that 0.5 atmospheres of oxygen are used. So that's the number that is reacted that I can use with a pressure ratio, just like a mole ratio. So atmospheres of oxygen on the bottom to cancel out, atmospheres of water on the top to give me what I want. And we get the numbers for my pressure ratio from a balanced chemical equation. So oxygen is 1 and water is 2. So that means that 1 atmosphere of water forms. Part B, same deal. This problem we could think of from the past as moles of hydrogen changes from 1 to 0.5 moles, and moles of oxygen changes from 1 to 0.75 moles. Find the formula, so we're just going to find a ratio of those moles of those pressures. So for hydrogen, there are 1 minus 0.50 is 0.50 atmospheres that are reacted, used. For oxygen, there's 1.00 minus 0.75 is 0.25 atmospheres of oxygen that are reacted. And all of that goes into the final formula. I was thinking about these 2's here and seeing what I want to do with that. I mean, since they're both 2, it doesn't matter. But if you wanted to, you could double that and say it would be like 1.0 atmospheres of H and 0.5 atmospheres of O. I guess that's what we would do if it was moles, but since they're both 2, it doesn't matter. Okay, so to find the ratio, you can divide both of them by a smaller number, so 0.25, 0.25, and so I get, there's 2 H's for every 1 O. So that's going to be the empirical formula H2O. Okay, part C. Mole fraction is moles of the things you're interested in over total moles. The mole fraction for nitrogen air is the same as the percent of nitrogen air, because usually percents are by mass, but the air one is actually by volume, which depends on the particles, which is moles. So that's why the fraction matches the percent. Okay, so mole fraction has a symbol chi. I think in Greek you say chi, but we say chi. And this is nitrogen, so that would be moles of nitrogen over total moles, which are moles of air. Moles of air, that says. And so, because pressure can be treated just like moles as long as temperature and volume are constant, I can say that this mole fraction is also equal to the partial pressure of nitrogen over the total pressure of air. And so then I have the total pressure, so I can use this as a conversion fraction to figure out the answer. So 761 millimeters of mercury, and then times, this is 0.78 millimeters of mercury of nitrogen over 1. It's 0.78 over 1. Millimeter mercury of air. That's how fractions work, is if they don't have something for the bottom, it's just 1. Okay, so this is the total pressure, so I'm trying to show you how the units cancel out because I'm trying to do a good job. Okay, so that would be 761 times 0.78 divided by 1. So that is 593.58. 0.78 is 26 figs. So that's going to be 590 millimeters of mercury. So in other words, I don't know if the fraction makes sense or not, but if, in other words, if 0.78 hundredths of 78 hundredths of the moles are nitrogen, then 78 hundredths of the pressure is also nitrogen. So you just multiply it by 0.78. Okay, last page. So we're doing some kind of reaction, making a gas in a flask. So this is water. Maybe it's like baking soda and vinegar or something like that. It's bubbling, making a gas. And then we have this connected to a tube. This tube seems hokey, but it's actually a real thing that people use for measuring like pressure in their gas lines and stuff like that if you're a plumber. There's also electronic versions, but they don't really have much advantage. So anyway, YouTube, and then we have some mercury in there, and if there was no pressure in there, the mercury levels would be equal, but because it's making some pressure in there, then the mercury got pushed up by 10 millimeters, so I'll label that 10 millimeters, and this is mercury, so the pressure unit then is 10 millimeters of mercury. And it says atmospheric pressure is 1 atmosphere, so that's the total pressure that's pushing down on this tube that's open. And then it says, what is the pressure of the gaseous product in here? So I want to know, what is the pressure in there? So, because the mercury is getting pushed this way, that means there's more pressure in here than there is outside. So I'm going to add, I'll write that down, more pressure inside than outside. So we need to add the pressures. Okay, so the total pressure in there.
Why do you need to write it instead of this? Put it all out on the printer.
It's too fast that way. We can't think that way. You have to write so people can think. If I just print it all out and say, here it is, they'll be like, great. You like it when people explain this stuff to you, or when people just say, there it is?
There it is.
There it is, yeah. Well, some of my students like that too. Okay, so that's why I'll take a picture also for you guys so you can just see. There it is, like Saya. Okay, so the total pressure in there, the pressure inside, total, I'm doing total because there's water in there too, gaseous water in there too, is going to be 1 atmosphere, which is 760, 3 figs, 760 millimeters of mercury.
Daddy?
Yes, me?
When I'm old up, can you buy me some gloves for touching chemicals when I'm rolled up, and a shirt that chemicals can get on it and not touch your and a shirt next to pants.
Oh, yeah.
Can you?
Made out of plastic?
Yeah, can you?
Mm.
That so the chemicals can't come through.
How about a hat to protect you from the chemicals? Is that a good idea?
Yeah, too.
And a mask to protect your face?
Yeah,
And goggles to protect your eyes?
yeah, all my body.
Okay, that's a good idea, sure.
So sometimes can you buy all that?
Yep, sounds good.
Okay, so that's when I'm alone.
Okay, so then we need to add our 10 millimeters of mercury that push this mercury up even more than the atmospheric pressure. So the total pressure inside is 770 millimeters of mercury, and then pressure inside that's just from the product that we're collecting, that means not the water also, is going to be the total minus the water, because the product plus the water is the total. So the total minus the water is the product. So that's going to be 770. We can use torr, I guess, doesn't matter. This one's in torr. Torr and millimeters of mercury are the same size of unit. 760 millimeters of mercury is 760 torr. They're not defined exactly the same way, but it doesn't really matter. Okay, and then subtract the partial pressure of water. That's from the equilibrium vapor pressure of water that we look up for the temperature of our experiment. It's given to us in the problem is 19.8 torr. So with sig figs, that's going to be 750 torr. When we subtract, I guess our calculator would say, sorry, we need a dot there. Our calculator would say 750.2 torr, but when you subtract, you keep the least number of digits after the decimal, which is 0, so we round to 750. Okay, almost done. Okay, this is just like the previous problem except for shorter. So it gives us atmospheric pressure, so it's collected over water. So we want to know what's the pressure of just the gas, as if it were dry. When the gas goes bubble, bubble, bubble through water, it gets wet, and then there's some pressure from water there too. So our equation is the pressure of the hydrogen plus the pressure of the water that comes with it when you collect it over water is the total pressure, which is equal to the pressure of the atmosphere in an open system. So that would mean that the pressure of just the hydrogen is the atmospheric pressure minus the equilibrium vapor pressure of water at the temperature of our experiment. So that's going to be 759.0 torr minus 19.8 torr. So that's going to be 750, 749.2, I think. Hopefully I did that right. 749, nope, 739.2 torr. Okay, last topic. All there is to this one is lighter gases effuse and diffuse faster, because if they're at the same temperature, then kinetic energy is, well, temperature is average kinetic energy. Kinetic energy is mass times 1/2 mass times velocity squared. So if things have different masses but the same kinetic energy, then the velocities have to be different. The heavier one has to have a slower velocity, and the lighter one has to have a faster velocity. Okay, so helium has a molar mass of 4 grams per mole, about, and nitrogen has a molar mass of 28 grams per mole. So helium is much lighter, so helium diffuses faster. So rubber is, I mean, everything has holes in it, but rubber, especially natural rubber, latex, has fairly significant holes in it, much, much, much bigger than atoms. Molecules, even kind of big molecules and viruses and stuff, can get through latex. We're going to say helium effuses faster. So if we start with equal amounts of helium and nitrogen, then over time helium leaks out, escapes through the hole because of its motion and contacting the hole faster. So eventually there's going to be more nitrogen left. Okay, and then this is not on your equation sheet. Sometimes this shows up on the AP test of this equation for calculating molar mass and effusion rate. So the equation is rate
Daddy?
of one gas. Yes, Amy?
These are all the ones we did.
Whoa, that's a lot.
Yeah, some of them are just normal papers with stuff on it. This one is not full out.
You want to show my students all the ones you made?
Yeah.
Whoa, a whole box of these. I don't know how to say that word. Embossed cards. Wow. Very cool. Good job, Amy.
Yeah, but do you want to see all the designs?
I want to see all the designs. Sure.
Okay.
Okay, I'm gonna pause.
You.
Okay, so the equation is rate of gas 1 over effusion rate of gas 2.
Daddy?
Yes, Minnie?
Do you know, well, what can they see your videos on?
Computers.
On their computers?
Yeah, they all have a little iPad. It's kind of like a computer phone.
Oh.
Okay, so. Oh, my other kid's waking up, so I'll be back. Okay, so I wasn't able to record for a while, so I just finished up the writing part. So the equation is rate 1 over rate 2 equals square root of molar mass of the second gas over molar mass of the first gas. So it flips the 1 and the 2. And I like to set it up so that it's a number bigger than 1. So instead of 1/4, I like to set it up so it's 4. So I called X, the gas we're trying to find, 1 and O2, 2. So then 4 is square root of 32 over the molar mass of gas 1. So square root both sides, and 16 equals 32 over molar mass of gas 1. Multiply both sides by molar mass of gas 1, divide both sides by 16, you get molar mass is 2. So that would be H2 is the unknown gas. And then I asked Ms. Block to add a separate question for 2A because I realized it didn't actually have changing conditions. So for this kind of problem, you can use the ideal gas law twice. That always works. Just solve for whatever you need and then plug it back in. Or you can use this one that kind of has the R's canceled out because they're always constant. P1 V1 over T1 N1 equals P2 V2 over T2 N2. So if you cross multiply, you get this, then you divide by everything that's not what you want to solve for, and you get this, and then plug everything in. Make sure you use Kelvin for temperature, and you get 27 liters at 2 sig figs. Hope this helps. You can text me if you have questions.